All right, guys, let's talk about 1.4. So we're going to go back over the basics of derivatives. Now, in Calculus 1, you spent probably half the class just talking about derivatives, and we're going to kind of refresh them in one lesson. So we're not going to go fast at all. And that is a little bit of humor. We're going to speed through this. I am going to pick and choose the things that we talk about and focus on the things that are going to be the most useful to you moving forward. So the first thing that I want to talk about, mainly because most of you are going into a physics or a heavy science background, is the difference between average velocity and instantaneous, between average value and a derivative. Okay. Now, back in college algebra and high school, you talked about slope. And depending on who you had for Calc 1, they may have told you that the derivative is the slope. And it is and it isn't. And I hope to tell you the difference between them, because mathematically that difference is not quite as important as it is in physics, engineering, chemistry, and all the other fields. So that's a very big thing that a lot of mathematicians may gloss over because they do not have the contextual understanding or contextual framework that the experience in those other fields to let them know, whoa, this is a way bigger deal than a math book may lead you to believe. So slope, if we just use this over here, is the rate of change between two locations. Now, most of the time it's drawn like this, and it's very easy to find. You just label your points. I'm going to call this x1, y1, x2, y2, and I'm just going to plug those guys in, and that's going to be a 1 and a 5, and that's going to be a -2 and a 0. So this will be 3/5 or 0.6. Now, here's what that means. This says that the whatever it is you have is going up by an average of 0.6 items per unit of time. So the number of doodads is going up by an average of 0.6 doodads per minute or second or hour, etc. Okay. Now, that is speed. Slope in real life is speed, otherwise known as rate of change. Rate of up or down. Change is just up or down. Rate is just speed. So how fast are you going up? How fast are you going down? How fast are you gaining items? How fast are you losing them? Whether that's money, whether that's production of parts, whether that's structural integrity, whatever that is. Now that's the average value. Okay, so just to give you a point of reference, from the time that I came into work when I used to work in a factory at 3 p.m. to the time my shift ended at 11 p.m., my average speed was 9 parts per hour on the machine that I ran. That was my average speed. I didn't make 9 parts every hour. Some hours it was 5, some hours it was 13, but I averaged 9 parts per hour. That was my production average I had to hit. So just because you have an average of a certain number doesn't mean you ever actually are that number. to average 9 parts per hour, I never actually have to make 9 parts per hour. I can make 8 and then 10, then 8 and then 10, then 6 and 12. I could go up and down and never actually hit that value. So that's something to keep in mind, because a lot of times if you go by this picture right here that we have of a straight line, which is what most people give you when you're dealing with slope, you're like, oh, well, that's just what it's always going to be. What we're really doing is saying from point A to point B, this could be the picture. Like, it doesn't have to be a straight line. And we're saying that the average speed of increase is 0.6. That's what we're saying. At no point does it ever technically have to be 0.6. Okay. Now, those of you math teachers who may be watching this video, yes, I understand that in a continuous function, if you're going above and below, at some point it does technically mathematically have to be 0.6. But a lot of times in real life, we're dealing with digital values. So we're dealing with discrete values and not analog or continuous values. So just throw that in there for any future math people who may be watching this going, oh, but what about the fundamental theorem of, I got you. All right. So let's look at this in a real world situation. And it doesn't have to be the average velocity like you might see in a physics class. It could be anything, the average. So right here, we have number of stores. So the number of stores in the United States for a given year, and I just stole this from Google, so I do not know how accurate this is. So please do not hold me against this. So I want to find the slope from 2002 to 2006. I want to find the average rate of increase. Okay, so this is going to be 2002, 5, and this is, or 6, I could just say 2, 5, and 6, looks like, let's just round that up to 35, but it looks like it's 34. All right, so I'm just going to plug that in. Average speed. Now remember, if the answer is negative, then it is going down. If the answer is positive, it's going up. And so that's going to be 35 minus 5, 6 minus 2. So that is 30 over 4, or 7.5. Now this is in thousands of stores. So every year, between 2002 and 2006, the U.S. gained an average of 7,500 stores per year. Boom. So when you're dealing with slope, you are dealing with the average increase or decrease between 2 moments in time. That's all it is. It doesn't tell you what's happening at a specific moment of time. And let's think 1600s, Newton's working on gravity. He doesn't want to know the speed of the apple between the time it leaves the tree and the time it hits his head. He wants to know the speed of the apple when it hits his head or when it hits the ground. So that's the big important key, is we are looking for the speed at specific single moments in time. And slope doesn't do that. Slope has to have 2 moments of time, and it just averaged between them. And you lose so much information. The more curvy your graph is, the more you lose when you try to find the average value, the slope. Okay. Now, instantaneous rate of change. This is what Newton and Leibniz worked on. Okay, Newton gets credit for it because he published it first. I do not personally think there's any way to know for sure who exactly developed it first, but Newton published first, so he gets the credit. And it uses a limit to shrink that down to where it is the slope at a single point, not the slope between 2 points, but the slope at a single point. And let's go ahead and work one of these. I know you worked a few of them in Calculus 1. I just want to work one more for you. And the main reason for that is because if all else fails, and you do not remember any of the other ways to find a derivative, this will always work. It will not be pleasant, but it will work. Because all the other methods to find a derivative are shortcuts of this. So this is a nice fallback. It's kind of like using quadratic formula to solve something to the second power. Is it the fastest way? No. Will it work? Yes. So it's always nice to have that tool in your toolbox. So the first thing we need is f of x, which we already have. And so that is 3x minus 7. Second thing we need is f of x plus h, and all we do is take the original and plug that x plus h in for it. Boom. Distribute the 3. And I am ready to plug into the equation. So the equation is the limit I got a mosquito on my screen. There we go. Mosquito dead. The limit as h approaches 0 of f of x plus h minus f of x divided by h. And so I'm just going to plug this in. This right here goes there. This right here goes here. And so this gives me the limit as h approaches 0 of 3x plus 3h minus 7 minus 3x minus 7 over h. Okay. Now you want to remember to distribute this. So the limit as h approaches 0 of 3x plus 3h minus 7 minus 3x plus 7 over h. Reduce the limit as h approaches 0 of 3h over h. And then the h's cancel out, and you're left with a 3. And that is the instantaneous slope. That is the slope at a single moment in time, not the average between two different times. Okay, so that is the thing that is the big difference between the two things. Slope, using the slope formula, is the average increase between two locations. Slope using the derivative is the increase or decrease at a specific singular moment in time. The exact moment it hits the ground. The exact moment the bat strikes the ball. Okay. All right. So right here, we have some of the shortcuts that you guys talked about in Calculus 1, and I'm going to add a couple more. I don't think I really have room, which is probably why I didn't add them the first time, but I do want to add that the derivative of just a number is always 0, and the derivative of a number times a letter is just the number. Okay, now if you have all of these memorized, you are in very good shape. Okay, these shortcuts will handle just about everything you can encounter. There will be more, don't get me wrong, but these are the majority. If it's not on this list, then your odds of encountering it are pretty small. unless you just happen to go into a very niche area. Okay. So let's look at this. So find the derivative. So the derivative is equal to the derivative of each individual piece. Okay, and so the derivative, this is a number times a letter. That's just going to be the number. And the derivative of a number itself is 0. So the derivative is 4. Cool. Now, if you were in class today, I didn't quite break it down that far. So if you're watching this and you've already had class today, there is going to be some slight differences. Okay. Just want to warn you ahead of time. Nothing wrong with how we went over it today in class. Just keep that in mind, that I'm being a little bit more specific on the lecture videos because I have unlimited time. All right, so let's look at the derivative of this. Now, this right here is something raised to a power. So when you're taking the derivative of something raised to a power, that's going to be power rule. Okay, so that exponent is going to come out front, and this will give us 3 times 4x minus 7 to the 3 minus 1. Okay. Now, one thing that you have to keep in mind is when you have taken the derivative of something with a parenthesis, you are going to have to do chain rule and take the derivative of the inside. Okay. Now, if we go back to the previous page, that's what all of this is. All of these. It's talking about taking the derivative of the inside. For each and every one of these, that's going to be chain rule. Okay. That is the number one thing that people leave out when they're taking derivatives. Do not be one of those people. Okay. Be careful. All right. So this is going to give us 3 4x minus 7 to the second power times 4. Putting the 3 and 4 together gives me 12 4x minus 7 squared. Okay. And so that right there is our formula for the derivative. Okay. And all we have to do is plug in a value for x, and that will tell us the slope at that specific moment in time. And that's what Newton was after. And that was the game change moment. When you're someone going into chemistry, physics, even biology to an extent, engineering, when you're going into these technical fields, finance, where you're doing a whole lot of calculations, especially involving how fast something's happening, it is the game change moment. There's nothing that compares. Okay. All right. Now let's do the natural log. And everyone always messes up on the natural log, so you want to be very careful. Now the derivative of the natural log is always 1 over what's inside. Always. Okay. This piece right here, no matter what it is going to come down. However, you got chain rule, so you're automatically going to have to multiply by the derivative of it as well, which means that when you're doing the logarithms, you do get a fraction, and you sometimes get a lot of cancellation. So sometimes a whole lot of stuff will reduce away. Not for this problem, but in general, you tend to get a lot of things that go away when you're doing logarithms. All right, there we go. And so that is the derivative of that logarithm, just one step at a time. Okay. So now let's look at trig functions. Trig functions are the same way. Notice how there's a parenthesis at the end. So that's going to be the integral. Actually, this one's a y. So that's going to be the derivative. Y prime is equal to dy dx sine 4x plus 7. Okay. Actually, it's a d. There we go. Make sure I didn't mess that up anywhere else. Okay. All right. And so that's going to give me y prime. Oh, I left off the 7. Okay. So the 7 comes down. The derivative of sine is cosine. The parenthesis comes down untouched. And then chain rule kicks in. I have to multiply by the derivative of the inside of the parenthesis. Okay. Never goes away. Chain rule just keeps coming back over and over and over again. So you want to be very careful about it. And then the 7 and the 4 can go together, and we can finish this out. There we go. Any questions about that one? Any questions at all? Okay. Now let's look at the product rule. Now, the product rule you guys talked about in Calc 1, you probably did not do that much with it. We're not either. You'll see a little bit of it in Calculus 3, just a little, where you see a lot of the product rule is once you start to get into Calc 4, differential equations, and you're doing separation of variables, you're doing second order homogeneous solutions, non-homogeneous solutions, complex solutions, actually all of them. Pretty much anything second order in Calculus 4 differential equations is going to have something times e to a power or something times a trig function or all three of them together, something times e to the power times a trig function. So you end up with product rule a lot in Calculus 4. So that's the main reason I want to go back over it, because when you get to Calculus 4, if you have it with us, I'll go back over it again because it'll be another year before you guys are in differential equations. But if you take Calc 2 with us like you're doing now and you transfer to another college, I don't know if they'll go back over it. So I want to hit it again now just to get it taken care of. So we are looking at the derivative of 5x cubed times e to the 4x. Okay, and if we look over here, that lays out the pattern. So it's going to be the derivative of the first item times the second item, not the derivative, plus the first item, not the derivative, times the derivative of the second item. And so that's going to give me 15x squared, that's just power rule, e to the 4x plus 5x cubed. Okay, so now let's take the derivative of e to a power. The derivative of e to a power is an exact copy of e. Boom. Times the derivative of the exponent. Think of the exponent as a parenthesis. So that's chain rule. Never goes away. So you definitely want to be careful about that. So that's going to be 15x squared e to the 4x plus 5x cubed e to the 4x times 4. Okay. And so the derivative is 15x squared e to the 4x plus 20x cubed e to the 4x. Now, I'm good with you stopping right there, but I do want to go ahead and get you used to the idea of continuing on. All we're doing right now is finding derivatives. When you're doing this type of stuff in Calc 4, you're going to be solving, and even in Calc 3, you're going to be solving after you're done with this step. So I want to go ahead and factor. I want to get you guys used to thinking about factoring all the time because it will help you a lot. So right here, I'm going to factor out a 5, an x squared, and an e to the x, or e to the 4x. So if I factor out what they have in common, then what's left behind is a 3 plus 4x. And that's going to be a whole lot easier to solve than what we had up above. Okay, so you do want to keep that in mind. All right, let's do one more. So we're going to find the derivative of this mess, 8x squared times sine 5x. So that is equal to the derivative of the first piece times the second piece, not the derivative, plus the first piece, not the derivative, times the derivative of the second piece. Okay. So that'll give me 16x sine 5x plus 8x squared. The derivative of sine is cosine. And you multiply by the derivative of the inside. So this gives me 16x sine 5x plus 8x squared cosine 5x times 5. And this gives me 16x sine 5x plus 40x squared cosine 5x. And if we factor, each piece has an 8 and an x that we can bring out. And there's our final answer. Just one piece at a time. Okay. All right. Now the quotient rule. The quotient rule is when you are dealing with the derivative of a fraction. So the derivative of a fraction is low d high minus high d low over low low. So we're going to do the low first, the bottom, 5x plus 2, d, which stands for derivative, high, which is the top. So low d high minus high d low. All of this over low low, which just means the bottom squared. And so that's going to give me 5x plus 2 times 3 minus 3x minus 7 times 5 over 5x plus 2 squared. So this is 15x plus 6 minus 15x plus 35. Now, where did that plus 35 come from? It came from distributing this subtraction sign. So you really want to be careful and distribute that subtraction sign. Okay, so let me do that in red. So take this and goes here and here. Okay, if someone has an incorrect answer for a quotient rule problem, the first place I look is that spot right there, the number at the end, to see if that subtraction sign was multiplied through correctly. I can reduce the top, and that gives me 41 over 5x plus 2. And so there is my derivative. Any questions about that one? Any questions at all? All right, I think we've got one more of these, and then we got a physics problem. Yeah. Okay, so let's do this one. I think this one's probably going to be a little more complicated. So low d high minus high d low over low low. So that gives me x squared plus 1 times 4 minus 4x minus 2 times 2x over x squared plus 1 squared. So this gives me 4x squared plus 4 minus 8x squared plus 4x over x squared plus 1 squared. So this gives me negative 4x squared plus 4x plus 4. over x squared plus 1 squared. Okay. Now, this particular problem right here does not reduce down any farther. Sometimes they do, sometimes they don't. That's actually kind of hard to figure out. What helps is having your factoring skills up. This right here almost but not quite factors to match the bottom. So I'm not going to go through it because it doesn't match. But if it did, then we would be able to reduce the bottom and the top and get a much smaller answer. All right, so let's look at physics. Now, in physics, when we're doing one-dimensional projectile motion, there are 3 spots we're trying to find. The first is the time to max height. So right up here is max height. But you can't just go and find it directly. You have to find this spot right here first, time to max height. So you have to find that first. Then that allows you to find this, which is very important. Now, not all things that make this parabolous frowny face shape are physics related. There's a lot of business that is also quadratically shaped, and that's not max height, that's maximum profit or maximum cost or maximum this. And we'll talk about this in Calculus 3 when we try to do maximums and minimums with saddle points, Lagrange multipliers. We'll talk about using derivatives to find not just the maximum height, but other maximums as well. And you did a little bit of this in Calculus 1 with optimization problems, where you're using the derivative to find the maximum amount that you can get out of what you have. Okay. Now, this part at the end, where it hits the ground, that's just going to be the 0. Now, it's called 0 for 0 height. You are at ground level. Okay, so that's why it's called 0. If you're talking about something going through the air, that's when you hit the ground. If you're talking about money, that's when you're broke. Okay, so it's when you have nothing. All right, so right here we have our trajectory, and just like it was before, this is a frowny face. That's the shape that it makes. So the first thing I'm going to do, find derivative. Now remember that the derivative is the speed, the velocity. So just by doing this, I have found the speed of the item. And if you take the derivative again, you'll find the acceleration of the item. All of those important things to have in physics. So once you have the derivative, step 2, find the time of max height by setting the derivative equal to 0. Okay, so that's going to be y prime is equal to negative 32t plus 480. 0 equals negative 32t plus 480. Negative 480 equals negative 32t, and 15 seconds is equal to t. So it takes 15 seconds to reach maximum height. And so now that I have that, I can actually find the maximum height. Find max height by plugging your answer from step 2 into the original equation. Okay, so I'm just going to plug that 15 seconds into the problem. And that will give me y is equal to negative 16, 15 squared plus 480 times 15 plus 4. So y is equal to 3604. So that is the maximum amount, the max height, 3604. Okay. Now, how to find when it's going to hit the ground? So that is step 4. Solve or set the original equation equal to 0 to find the 0, which in real life is when it hits the ground. Okay, so that's y equals negative 16 t squared plus 480 t plus 4. Set that equal to 0. And then I'm going to use the quadratic formula to solve this. And that's going to be t equals negative b plus or minus b squared minus 4ac over 2a. So t is equal to negative 480 plus or minus 480 squared minus 4 times negative 16 times 4 all over 2 times negative 16. So I'm going to get two answers for this. The first is negative 0.008 seconds. And the second is 30.008 seconds. So that is when it's going to hit the ground. If you want to find the speed when it hits the ground, just plug it into the velocity. So v equals negative 32t plus 480 So when this object hits the ground, it will have a speed of negative 480.256. That's probably meters per second. Okay. All right. Well, I think that finishes up. Yep. The next page is a blank page in case I needed it to finish up. All right. So I think that finishes that up. I'll stop right there, see if anybody has any questions. And then I think our next video will be over integrals. All right. Yep. You guys have a good day.